What I want to talk about in this video are the notions of electronegativity, negativity, and a closely related idea of electron affinity. Electron affinity. And they're so closely related that in general, if something has a high electronegativity, they have a high electron affinity. But what does this mean? Well, electron affinity is how much does that atom attract electrons? How much does it like electrons? Does it maybe want more electrons? Electronegativity is a little bit more specific. It's when that atom is part of a covalent bond, when it is sharing electrons with another atom. How likely is it, or how badly does it want to hog the electrons in that covalent bond? Now, what do I mean by hogging electrons? So let me write this down. So how badly wants to hog, and this is an informal definition clearly, hog electrons. Keep the electrons to spend more of their time closer to them than to the other party in the covalent bond. And this is how much they like attract electrons, or how much affinity they have towards electrons. So how much they want electrons. And you can see that these are very related notions. This is within the context of a covalent bond, how much electron affinity is there. Well, this, you could think of it as a slightly broader notion, but these two trends go absolutely in line with each other. And to just think about electronegativity, make it a little bit more tangible, let's think about one of the most famous sets of covalent bonds, and that's what you see in a water molecule. Water, as you probably know, is H2O. You have an oxygen atom, and you have two hydrogens. Each of the hydrogens have one valence electron, and the oxygen has, we see here in its outermost shell, it has 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6 valence electrons. And so you could imagine hydrogen would be happy if it was able to somehow pretend like it had another electron. Then it would have an electron configuration, a stable first shell that only requires 2 electrons. The rest of them require 8. Hydrogen would feel, hey, I'm stable like helium if it could get another electron. And oxygen would feel, hey, I'm stable like neon if I could get 2 more electrons. And so what happens is they share each other's electrons. This electron could be shared in conjunction with this electron for this hydrogen. So that hydrogen can kind of feel like it's using both and it gets more stable. It stabilizes the outer shell, or it stabilizes the hydrogen. And likewise, that electron can be shared with the hydrogen, and the hydrogen can kind of feel more like helium. And then this oxygen can feel like it's a quid pro quo. It's getting something exchanged for something else. It's getting an electron. It's sharing an electron from each of these hydrogens, and so it can feel like it's that it stabilizes it similar to a neon. But when you have these covalent bonds, only in the case where they're equally electronegative would you have a case where maybe they're sharing. Even there, what happens in the rest of the molecule might matter. But when you have something like this, where you have oxygen and hydrogen, they don't have the same electronegativity. Oxygen likes to hog electrons more than hydrogen does. And so these electrons are not going to spend an even amount of time. Here I did it kind of just drawing these valence electrons as these dots. But as we know, the electrons are in this kind of blur around the actual nuclei, around the atoms that make up the atoms. And so in this type of a covalent bond, the electrons, the 2 electrons that this bond represents, are going to spend more time around the oxygen than they are going to spend around the hydrogen. And these 2 electrons are going to spend more time around the oxygen than are going to spend around the hydrogen. And we know that because oxygen is more electronegative. And we'll talk about the trends in a second. But this is a really important idea in chemistry, and especially later on as you study organic chemistry. Because we know that oxygen is more electronegative, and the electrons spend more time around oxygen than around hydrogen, it creates a partial negative charge on this side and partial positive charges on this side right over here, which is why water has many of the properties that it does. And we go into much more depth in that in other videos. And also, when you study organic chemistry, a lot of the likely reactions that are going to happen can be predicted, or a lot of the likely molecules that form can be predicted based on electronegativity. And especially when you start going into oxidation numbers and things like that, electronegativity will tell you a lot. So now that we know what electronegativity is, let's think a little bit about what is, as we go through a period, let's say as we start in group 1 and we go to group, and as we go all the way to, let's say, the halogens, all the way up to the yellow column right over here, what do you think is going to be the trend for electronegativity? And once again, one way to think about it is think about the extremes. Think about sodium and think about chlorine. And I encourage you to pause the video and think about that. Assuming you've had a go at it. And it's in some ways the same idea, or it's a similar idea as ionization energy. Something like sodium has only one electron in its outermost shell. It would be hard for it to complete that shell. And so to get to a stable state, it's much easier for it to give away that one electron that it has so it can get to a stable configuration like neon. So this one really wants to give away an electron. And we saw in the video on ionization energy, that's why this has a low ionization energy. It doesn't take much energy in a gaseous state to remove an electron from sodium. But chlorine is the opposite. It's only one away from completing its shell. The last thing it wants to do is give away an electron. It wants an electron really, 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 really badly so it can get to a configuration of argon, so it can complete its third shell. So the logic here is that sodium wouldn't mind giving away an electron, while chlorine really would love an electron. So chlorine is more likely to hog electrons, while sodium is very unlikely to hog electrons. So this trend right here, when you go from the left to the right, your electronegativity, let me write this, you're getting more electronegative. More electronegative as you go to the right. Now, what do you think the trend is going to be as you go down in a group? What do you think the trend is going to be as you go down? Well, I'll give you a hint. Think about atomic radii. And given that, pause the video and think about what do you think the trend is? Are we going to get more or less electronegative as we move down? So once again, I'm assuming you've given a go at it. So as we know from the video on atomic radii, our atom is getting larger and larger and larger as we add more and more and more shells. And so cesium has one electron in its outermost shell, in the sixth shell, while, say, lithium has one electron. Everything here, all the group 1 elements, have one electron in its outermost shell, but that 55th electron, that one electron in the outermost shell in cesium, is a lot further away than the outermost electron in lithium or in hydrogen. And so because of that, well, one, there's more interference between that electron and the nucleus from all the electrons in between them, and also it's just further away, so it's easier to kind of grab it off. So cesium is very likely to give up electrons. It's much more likely to give up electrons than hydrogen. So as you go down a given group, you're becoming less electronegative. So based on this, what are going to be the most electronegative of all of the atoms? Well, they're going to be the ones that are in the top and the right of the periodic table. They're going to be these right over here. These are going to be the most electronegative. Sometimes we don't think as much about the noble gases because they aren't really that reactive. They don't even form covalent bonds because they're just happy. Well, these characters up here, they sometimes will form covalent bonds. And when they do, they really like to hog those electrons. And what are the least electronegative, sometimes called very electropositive? Well, these things down here in the bottom left. These over here, they have only, in the case of cesium, they have one electron to give away that would take them to a stable state like xenon. Or in the case of in these group 2 elements, they might have to give away 2, but it's much easier to give away 2 than to gain a whole bunch of them. And they're big atoms, so those outermost electrons are getting less attracted to the positive nucleus. So the trend in the periodic table, as you go from the bottom left to the top right, you're getting more more electronegative.